morning, ladies and gentlemen. My name is Hans Peter Nehe, and I will be your chairman for this session on medium voltage converters. We have 4 interesting papers, and the first presenter here is Jacek Radkowski from Warsaw University of Technology, and he will tell us a little bit on insights into the turn-off process of silicon carbide MOSFET power modules. Please.
Thank you. Welcome, everyone. First of all, I would like to say thanks to Mietek for the invitation. It's really great to be here again. And also, it's also the pleasure to speak not online and to see your faces and see the feedback from the audience. So, as Hans-Peter mentioned, I'm going to talk about the turn-off process of SiC MOSFET. Then I will also show you the 2 methods how to find the channel current. Then I will present a brief study on 400 kV DC-DC converter. And finally, I will summarize my talk. The whole work was done in the frame of the project that you can see is Reset for Rail. We are together with colleagues from Ikerlan in Spain in this task that we investigating the silicon carbide power devices for wireless charging. So, basically, I'm gonna talk about the soft switch converters. Because if you're using the SiC MOSFETs and power modules for hard switching, the turn off is not that important because the most of the loss then appears at turn on, of course, right? But we have soft switch converters, including those for wireless power transfer, for chargers also. We can name several applications. So obviously there are resonant ones, as you can see on the slide, a dual active bridge, but also, as was presented yesterday, we can also operate with the triangular current mode or critical current mode, whatever you call it, with the DC-DC or AC-DC converter. So there is a group of soft switch converters, and in this group, one component of the loss is like conduction, and the other is mostly related to the turn off. And as you can see, mostly this, we multiply the switching frequency by turn off energy. So what's the problem then? Let's just find the data sheet for our module and use this value which should be provided by manufacturer. Usually they obviously do the double pulse test and it shouldn't be a problem. But there is a problem because we can split the drain current during turn off for 2 components. I apologize to the device people for this simplification because it's not that easy as in the drawing, but basically we have the channel current component and let's say this capacitive component. And I marked the channel current in red because it causes loss, and the rest does not. So basically to identify and estimate the loss, we need to know the channel current, not the drain current. More or less, if we skip the ringing, the waveforms looks as on this drawing. So we have a voltage, drain source voltage rise, the drain current, and inside the drain current we have this dashed line, which is channel current, and of course this capacitive current. It more or less look like that. So as I said, it's for sure that this is gonna be the turn-off energy will be lower than this multiplication of the VDS and ID. In some cases, we can reach near, because this capacitance is like a snubber, so we can reach the nearly lossless switching. But for the power modules, I'm talking about the power modules rated at hundreds amps. We obviously have a few chips in parallel, and also the chips have a big chip size, so then they are also rated at 1700 or 3.3 kV. So basically, we have a huge capacitance inside. So it's rather this lossless switching is not possible. Also, we have the gate current limitation, because even if devices is rated at 5 amp or 500 amps, we still have a, here you can see the circuit and the equation for the gate current. So we still have the maximum and minimum gate voltage the same, right? And of course, you can play with the gate drivers and so on and so far, but at the end of the day, it's not that easy to use like 50 amp. It's always going to be a few amps in the gate driver. So basically, for the power module, typical waveforms look like that. That we have the voltage rise and the channel current here, and after that, when the voltage reaches maximum, we still have some remaining current here. And of course, you can see the difference in the waveform. So basically, what we did, we've been trying to find and identify the channel current to recognize the real or actual of loss. Yeah, that's the waveform for 900 amp 1.7 kV module. So you can see basically for the VDS reaching the DC voltage, we still have in each case, if it's faster, slower, higher current, lower current, we still have some current left here, generating loss, of course. So the first method to find the channel current is obviously to use the transfer characteristic, follow the gate source voltage, and use those characteristics. So that's just looks very simple, but as we heard in the first presentation, then also in the previous presentation, there are different effects in silicon carbide MOSFET, and of course, if I will go to the data sheet and take the transfer characteristic, this is just one version of the whole family of the characteristic, because we have several factors influencing this characteristic. So we tested this issue. I'm not going that much into details now. The point is that to find the channel current, you need to have a transfer characteristic measured in similar condition than in your operating system. So we just made like single pulse test with inductive load, and on the falling slope of the current, we measure the transfer characteristic, and as you can see, there is a dependence on the drain source voltage, and it's quite big, I would say. This is most likely because of the drain-induced barrier lowering. So we have a dependence on the drain source voltage. The other thing was mentioned before, charge traps below the oxide. So here you can see the pulse with the resistive load. So depending on the length of the pulse of the maximum positive voltage applied before turn off, you're getting different transfer characteristics, right? But I'm not going to discuss this in details, but for sure we have this dependence also. So basically, the things are quite complicated, but we done a number of tests. We gather all those characteristics, and we run the module in the half bridge with inductive load. It emulates this soft switch system. So we have a basically similar waveform, and we applied those characteristics to identify the channel current. So you can see gate source, drain source voltage, and the blue is the drain current, and dashed line is the estimated channel current. The red is capacitive current. So I would say that with this method we are close to reality. But we've been not that much satisfied with this method. So the other method is to use the VDS slope and capacitance characteristics. So it's just much simpler. The only condition is that you need to have this characteristic capacitance versus drain source voltage, which is for this high voltage or medium voltage power modules is not so common. Then you just measure VDS, calculate the capacitive current, and then it's easy to find the channel current as a difference between the drain current and capacitive current. So the same module, different test conditions using this second method. So what we can see is basically that for low current, right here was like 120. The difference between drain and channel current is pretty significant. For higher current, of course, is lower. So we've done number of tests again. For 900 amp module and also for 800 3.3, and you can see the difference between the energy calculated in the regular way from the drain current and energy calculated from the channel current. So for different switching speeds, for different currents, basically as faster is switch, the difference is bigger. The lower current is, again, the difference is bigger. So I would say that this issue cannot be neglected for sure for those type of power modules. And just to not end with this slide, I just made a very rough calculation of the power loss for like two-phase DC-DC converter. Basically, we're doing something similar for the energy storage. So it connects the 800 volts DC link with 1.5 kV battery. So as I said, you can run this system in this triangular current mode. Using two modules, only 50 micro Henry of inductance, of course rated at high current, because this is like 400 kilowatt system. Basically, with this control, the input current should be pretty smooth. But we are not going to talk about this converter. Let's have a look at the loss. So basically, this bar is EOF calculated for 500 amps for the nominal power. So the blue is the conduction, and this bar is switching. And when I use EOF, according to my estimation, I have a 13.5% of difference. Then with this control, when I reduce the current to maintain this critical conduction mode, I need to increase the switching frequency. Then, of course, the share of the switching loss is much higher in comparison to conduction loss. And then, as you can see, the difference is 1/3 of the energy. So now, designing the heatsink, doing this electrothermal design, I think that at least for these high power modules, we need to take into account this issue. So to summarize my talk, so as I said, this turn-off process is essential for soft switch converters. Only the channel current, mostly the channel current cause the loss. We have basically two methods to identify this channel current. We prefer this method based on dV/dt. And I believe that this is very important for the thermal design, and basically this simple calculation for this DC-DC converter confirms my opinion. Of course, you can always oversize your heatsink, but what for? Thank you for your attention.
Thank you very much. So, any questions? Okay.
The question is that when between these
Maybe take the microphone.
between these two methods that you have introduced, you have said that dV/dt is much more precise. Have you calculated how much deviation you have in the first method?
Yeah, but the point is that as we've seen before, all those things with the like charge traps, what we realize that it's so many factors. It's like VDS, VGS, also the shape of VGL's pulse, the length of VGA's pulse. So basically, it's even hard to gather also the junction temperature, right? So basically, what we've seen is that the waveform looks reasonable, but we cannot even estimate how precise it is.
The first method, even in the second method, or?
Yeah, the second method is just depends on the good measurement, and basically the voltage is the voltage probe, non-isolated probe, has better bandwidth than the current probe. So
I don't think so. The second method will be independent of the temperature.
yes, it might be dependent, but I'm afraid that this is rather a question to the someone who is much more familiar with the device design and stuff like this.
Okay, thank you.
Thank you.
I was just curious about when you measure the voltage, you also have a stray inductance. So the voltage you have, so to say, on the capacitor on the chip is not the same as the voltage you measure on the module. Do you see any problems there?
Yes, of course. I was not mentioning those details because for the first method, you have to also use the internal gate source voltage, not the external one. And also for the voltage, you need to synchronize properly voltage with the current, and also you need to remove this voltage drops across the inductances. We did it, of course.
Very good. So I think we've run out of time now. We thank the speaker.
Thank you.
So our next speaker is Stefanie Heineck from Hitachi Energy. She will talk about experimental insights into the megawatt range dual active bridge with silicon carbide devices. Please, Stephanie.
Thank you, Hansi. Yeah, welcome everybody from my side. Let me quickly introduce myself. 1.5 years ago, I finished my PhD under supervision of Hans-Peter Neh here at KTH. Not here, in Stockholm at KTH. That was on the topic of modular multi-level converters for HVDC grids. And right after that, I joined back then called Hitachi, ABB Hitachi Power Grids in Turgi in Switzerland, where we work on medium voltage converters. And thanks to the organizers for your invitation to present our work here on a solid state transformer with silicon carbide devices. I prepared the following agenda for you today. I would like to start out to give a bit of background and context of the application of solid state transformers. And then I will continue by presenting the main circuit elements and some details of our experimental setup. Continuing with details on the used modulation and control scheme. And the heart of the presentation will be here about the experimental results that we could achieve. A heat run, continuous operation, some detail about our in-house anti-saturation control, and then a loss comparison that we did based on calorimetric measurements and some simulation results. And then I would like to summarize the talk. So the background was basically kindly given already by Professor Bhattacharya just before. So the solid state transformer is quite hot topic, even though the technology is rather old, some decades ago. But the momentum of DC grids that are discussed right now to integrate decentralized sources and loads and energy storage. In this context, the solid state transformer, because it is an isolated DC-DC converter, will be the key component, and that's why there's a lot of discussion about it right now. The dual active bridge topology is one potential candidate next to resonant topology, so you can have also LLC topology. But the dual active bridge gives some interesting benefits like wide voltage range controllability and scalability. That's why we focused our work on the DAB topology. You see a schematic of a DAB cell here below. It's well known. We used the basic form of having 2 full bridges, so not a 3-level topology, but we have 2 full bridges connected via the MFT. And the goal for us was, for our laboratory demonstrator, we wanted to build a quite high power DAB cell, 0.5 megawatt, with in-house silicon carbide devices and also in-house medium frequency transformer. So our unit collaborated here with the transformer unit in Geneva, Hitachi Energy Geneva. So the 2 main circuit elements are the MFT and the semiconductor devices. So here I would like to present you which technology we used. Medium transformer, as mentioned, in-house developed. We saw already in presentations before how volume and weight can be reduced by higher switching frequency. This is quite obvious. But the design challenges that come with medium voltage, I want to point out here. So medium voltage insulation design is not trivial. And also the medium frequency losses, to manage them, like proximity skin and core losses, are really not easy. There are 2 types that are currently developed in Geneva. We have the oil MFT and the dry type MFT. In the demonstrator in our lab, we used the oil type MFT. It's also water cooled. In the future, we will test also the dry cast MFT, but all the results that I will present to you now are based on the oil MFT. Furthermore, we use the SiC Limpec semiconductor devices, also in-house developed in our fab in Lenzburg. That's an open standard. You see, I guess you are very familiar with this type of module. You can see it from other suppliers, different names. Features low internal strain inductance, so it's made for silicon carbide. high current densities, and Hitachi Energy offers this device in 2 voltage classes, 1.7 and 3.3. That's also the 2 that we used in our setup. On this slide, you see some more information about the experimental setup that we used. The table summarizes the ratings. 550 kV rated power, DC link, primary side 2.5 kV and 1.2 on the secondary side. I would like to mention the wide frequency range. So we discussed with the colleagues in Geneva that we would like to test many different operating points. So we have here a rather big range. For a product, you would like to go more for dedicated frequency to optimize the transformer design. But the whole demonstrator was really for learning purposes and for testing of several operating points. So you can see also it's not designed to be very compact, but rather for easy measurement, modular DC banks you can see here on the left and right. So we can quickly change the capacitances. In the middle you have the MFT below the setup, and the semiconductor devices and the AC link are here below the classes. What you can also see on this picture that we have 2 DAB cells so that we can operate the whole setup in a back-to-back configuration. One cell is the silicon IGBT, and the other cell is silicon carbide SiC. So we wanted to test both to compare the performance. In the top one, cell 1 controls the DC link voltage, and the second cell controls the circulating current. And that's quite nice because in this back-to-back configuration with our source, we only have to feed the losses of the system, and we can don't need very much energy to run this experiment. Here a few words about the used modulation and control scheme. We decided to go for a very conventional approach for the control, so there's no surprises here. We have conventional phase shift modulation. So we switch all the 4 half bridges 50% duty cycle, and by that we can control the current with 2 or 3 we can reach 2 or 3 voltage levels. The closed loop control is classic cascaded approach. We have inner current control loop of the MFT current, so we can control active power. This will give a phase shift set point to the modulator, which in turn sends the switching signals to the devices. And we have an outer control loop, which controls the voltage on the secondary side and outputs the current set point. A few more words to the anti-saturation control. Here we put some effort because we wanted to avoid any DC blocking capacitors in the DAB to avoid saturation of the core. But for this, you really have to put some effort to control the offset of the magnetizing current to 0, that the core will not saturate over time. And we did that by measuring the AC currents on the primary and on the secondary side of the MFT. The difference gives us the magnetizing current, and if we sample then the maximum and minima, we can calculate the mean value, which we then, with the PI control, control to 0 by some minor duty cycle corrections. And the results, also the working of the controller, I can present you on this slide. So before the dashed line here on the left side, you see the computed maximum and minimum magnetizing current, and you can clearly see there is a slight offset. So without any DC blocking capacitors, over time you would saturate the MFT. Here, at that point, we turned on the anti-saturation controller, and you see the dynamics after 2 microseconds. We can nicely control this DC offset to 0 and avoid saturation. Interesting observation from the lab was here that we have, after turning on the control, the acoustic noise in our lab was drastically reduced. So if you have some magnetizing current, the core vibrations are, you can hear it acoustically. So that was maybe worth mentioning. Here now the experimental results in terms of electric measurement and calorimetric measurements. I have to say, for this hybrid operation with the silicon carbide and silicon IGBTs, we had to reduce a bit from the maximum power because the silicon IGBTs would get else too hot. So we used here in this comparison this described set point, 360 kilovolt. Also, I would like to mention that we switched the silicon carbide cell with 4 kilohertz and the silicon IGBT cell with 2.5 kilohertz. And here is a snapshot of the experimental results for the silicon carbide cell. The calorimetric measurements we installed for the two bridges. So we measured here the sum of switching and conduction losses by measuring the dissipated power into the water. So we have flow rate measurements and temperature sensors in our setup. And then since the power is a function of this delta T, of inlet and outlet water temperature and water flow rate, we could calculate the dissipated power. In 2 slides from now, I show you some bar charts, so it's easier to read, but the numbers you can see already in this table. For the loss comparison, I would like to spend some time on this slide to describe how we compared the two simulation results. We have an in-house design tool based on MATLAB Simulink, where we replicated the demonstrator setup. It's like these two cells in back-to-back configuration, and also the devices that we used. So we modeled conduction losses based on datasheet values. But for the switching losses, we had to pay attention because we found out in prior done double pulse tests, as here on the right-hand side, that there is, for the IGBT, this dynamic scene. It's also referred in literature as charge memory effect, that you can see a reduced switching energy with higher dIdt prior to switching. That was also presented by Hans-Peter Neher and Per Ranstadt 2011. So the internal charge dynamics of the IGBT should be considered here in the simulation, else you would get wrong switching loss results. In our case, we see here for the 3.3 kV IGBT that we have 80 amps per microsecond the IDT before we switch off, which, if you check on the right-hand side here, this translates to a reduction factor of 1.7 switching loss reduction because of this high DIDT, and that we incorporated into the simulation. Now comparing the simulation and the calorimetric measurement, here in this bar chart, the red reflects the switching losses in the simulation, blue the conduction losses in the simulation, and in gray calorimetric measurements from our demonstrator. You notice that the match is pretty good. But I would like to note 2 things. The 3.3 kilovolt devices are quite oversized here in our demonstrator. That's why we see lower conduction losses relatively compared to the 1.7. And also one should consider, because of the back-to-back operation, that the full bridges are either in inverter or in rectifier mode, so there's also a difference. So these columns, we have to be careful to compare them directly, so rather individually. Also, the switching loss advantage of the silicon carbide is more pronounced for the higher voltage. This can be easily explained because in general, SiC has much less stored charge because it's a unipolar device, but this factor is particularly pronounced for the higher voltage devices. And also, interesting finding here that despite we switch 4 kilohertz instead of 2.5 for the silicon carbide, you see that we have a better efficiency compared to silicon. In our case, the MFT had 700 watt losses. Let me conclude on this slide what has been achieved. We did calorimetric loss measurements of the semiconductors in the SST setup here. We measured a pretty high efficiency of 99.2% for silicon carbide semiconductors and 98.4% for the silicon. And we showed you, or I showed an efficient way to achieve the anti-saturation control to avoid any additional components like the DC blocking capacitors for the DAB. Also, I would like to mention we have published the results that I presented here in IPEC ECC Asia, which is just at the moment running conference in Himeji. So if you would like to have more information, you can turn to this paper. What are the prospects? So you have seen here the elementary DAB cell. You can combine these cells in ISOP or IPOS configuration, and then you can reach megawatt LVDC to MVDC conversion. And yeah, you can foresee various application as integration of renewable energies into the power system via DC links, as described also by Professor Bhattacharya. Yeah, that was it from my side. Thank you for your attention, and I'm open for your question or feedback.
Thank you very much. So, any questions? Yes?
The 3.3 silicon carbide MOSFETs, are they internal to Hitachi, or did you buy them from an outside source?
We got them internally, but we also tested the Mitsubishi one.
The Mitsubishi 3.3 kV module, or?
Yes, also in this in the same package.
Okay, but those are not commercially available as modules or devices, right?
I think they are.
Okay. Okay, thank you.
Yes, yes.
So, we have time for more? Yes?
When you are combining basically the converters in ESOP or IPOS configuration, the middle voltage transformer basically needs to block always the highest voltage. As basically in case of failures and for redundancy reasons, you always need to ensure that you have the full blocking capability. Where do you see limitations in terms of voltage within the transformer which you have shown?
In which part of the transformer? Or in
So if you work with 2 kilovolt, you can basically cope with the size of the transformer as you have shown. If you go now to, let's say, 10 kilovolt,
but
you need
design was for 10 kilovolt.
this was for 10 kilovolt. Okay, so all the spacings and isolation
yes,
and partial discharge is already designed for 10 kilovolt. Okay.
And for the lightning impulse, I mean, they are standardized, the test voltages. We have to go even higher then.
Okay, thanks.
So, we have time for one more short question. Okay, we don't have more questions. Then let us thank the speaker.
Thank you.
Okay, our next speaker is Ole Christiansbro from NTNU in Trondheim. He will talk about design and optimization of an auxiliary power supply with medium voltage isolation using GaN HEMTs. Please.
Thank you. Also thank you to the organizers for giving me this opportunity to present a summary of my PhD work. So it will be a speed run through the most important findings. we set out with a gallium nitride component and said, okay, where can we find a possible application where the gallium nitride could shine or could make a big difference? So we went to design a auxiliary power to supply gate power in a medium voltage converter. So for this presentation, we'll just give a brief overview of the application, then go into the transformer design, and then over to the topology selection, and then some final words on going from the proving the concept into what an integrated prototype can look like, and give a short conclusion. So medium voltage converters becoming increasingly interesting for many industrial applications, e-mobility. So you can have a range of different converters. Here I'm showing a multi-level type converter where you have several sub-modules, which could, for example, contain a full bridge silicon carbide MOSFET converter, which needs some gate power, electronic sensors, and you could feed that from the DC link itself, or for some system benefits, you could choose to supply it from an external voltage source or energy source. But then you would need an isolated power supply that is related to the DC link, the full DC link voltage. So it gives very hard criteria for the isolation barrier that we have to provide, so that medium voltage isolation. In addition, we would like to have a low coupling capacitance over that isolation barrier, because each time we have a switching incident, we get circulating noise currents. We want to limit that capacitance. So to do this, we chose a magnetic transformer. And you can do it in many different ways, but this was our choice. We could go for a planar option, which becomes challenging to design when you go to these high voltage levels for the dielectric design, or the more traditional winded option gives a larger size and weight and includes manual production steps. So we're trying to go away for that, and we go for the planar option, drawing on experience on sort of wireless power supply type of concepts. So we can have a helical PCB printed winding, or spiral windings per PCB layer, or a single helical winding. And then we can take a cross-section of that, and then we can represent that geometry in a 2D axial symmetric way. So you see, we'll have on the primary side, we'll have a PCB with a number of printed windings and, in layers and turns. We chose a solid dielectric material in between, and then we have the secondary side mirrored. So we're also choosing a coreless concept to really focus on that voltage isolation part. Now, using printed windings, we have very easy manufacturing, high repeatability. That's good for making products. But there's one disadvantage, which I'll come to in the next slide. Since we have a coreless design, we have a real incentive to go to very high frequencies, because we don't have the magnetics to worry about. So we'll go for smaller size. The transformer efficiency will be proportional to the frequency of operation. And so we went for 6.78 megahertz, which is the first allowed frequency band in terms of emissions. And that's also why you find wireless power operating in the same band. So again, the disadvantage, if we look back into this cross-section of these windings, in terms of dielectric design, here we have a cross-section of the outer winding, so 35 micrometer copper, and we have a very, very sharp edge around that copper. And so we have a very, very high electric field amplification just around that corner, so that's going to be our weak spot in terms of dielectric breakdown. So you see the high field in the corner, and it continues into the dielectric, which we choose Teflon for this work. And we looked into several ways of grading that field, of alleviating the high field option. And the best option was permittivity field grading. meaning that we will cover the copper in a epoxy or some other material that has a much higher permittivity than the dielectric. So Teflon has around 2, so solder mask naturally has around 4, and then we can try to find other materials that have even higher. So for the work, we would buy bare PCBs and we would cover it with a high permittivity epoxy upwards to 9, 10. And what this will do is push the high electric field over a greater area, and you get the lower peak value. Now, we tested this concept in breakdown testing. So we tested with 2 things, different thicknesses of the dielectric, and also this permittivity field grading option and other options. So just quickly, we had 1 millimeter, 3 millimeter, 6 millimeter Teflon with identical windings on primary, secondary side. We can see that as we go to higher thicknesses with different winding structures that are optimized for efficiency, we can increase the breakdown voltage, and these breakdown values by the standards allows it to operate well into the medium voltage range. So we can choose the thickness depending on the criteria. And in addition, testing the permittivity field grading concept, we only did that for the 1 millimeter. So the normal here is with just a solder mask covering, and using the epoxy, we could show a improved performance, a more consistent breakdown voltage. And I would expect that improvement to increase with thicker Teflon or dielectric thicknesses. So we showed that the transformer concept can work for the voltage level that we're targeting, but now we have a coreless design, so we have a very high leakage inductance. And so we have to incorporate that into the topology choice for the auxiliary power converter, among other things that we want from it. So I'm just going to show you quickly the overview of the topology that we chose, and then I'll say why we chose it. So it's a DC-DC resonant converter. We have a common DC input voltage of 48 volts. We have an output voltage that's relevant for driving silicon carbide MOSFETs. The power requirement approximately for that full bridge setup, and the frequency as described. So we have a gallium nitride inverter, so it's packaged inside the same AC with the drivers, making it very compact. And then we feed that into a LCC resonant tank before we have the transformer. And then we have a resonant Class E rectifier using silicon carbide Schottky diodes because of their low capacitance. And I'll go through why the resonant tank and the dimensioning of the rectifier. So since we're operating at such high frequency, PWM regulation is quite challenging. So we try to find we use a resonant power converter topology, but now the operation of the converter will be load dependent. So we have to find a combination that gives us an appropriate load line at the output without losing soft switching. And this topology will do that. So you'll see from the trapezoidal input voltage from the half bridge will be in the black here, 48 volts. And as we're decreasing the load resistance, the in-phase current will increase, but the current at the switching instant is constant, and that's what the solid orange line shows. However, if the load will also change its reactive component, we will have a difference in the switching current, and so we could potentially lose the soft switching. So we have to include that into the design. And so to this resonant rectifier class, a series L class rectifier. So the L is in series with the diode and the resonant capacitor. So it has very few discrete elements. Actually, we're using the secondary winding of the transformer as the L. So we only have a capacitor and the diode. And we want some capacitance in addition to the diode to have a more linear behavior. To explain a little bit the performance, I just want to define the voltage transfer function. It's the relation between the DC output voltage and the AC voltage fed into it, and also the resonance frequency, tuned resonance frequency of these elements. So normally you would design this thing to resonate at the switching frequency, but actually going for double the switching frequency gives us a lot of benefits for the application. And some disadvantages. So we'll have some factor A times the switching frequency. That will be the dimensioning frequency. And so we show here a plot for 1.5 up to 2 times the switching frequency. And then we have the voltage transfer function. So higher would be better. So we see it as we go from 1.5 down to 2. We'll lose some of the transfer function, which loses some efficiency. Let's very quickly said. But what we also see is that if we look at the output power, output voltage of the rectifier, it becomes very flat. So if we have a nominal voltage at nominal power output, for higher resonance frequencies, we have a very, very flat output voltage. We have a very, very nice load line coming out of the rectifier. This is a great advantage for the application and the stability. So we can sacrifice some efficiency. We get the load line. We get smaller passives, smaller size. I'm not going to go into the other details, but you can also show that there's lower variation in the reactive component of the operation of this rectifier. So this is preferential, as we said, for the soft switching operation of the converter. But now we have a tuned second harmonic. So we have a lot of circulating currents with higher harmonic numbers. Linear analysis sort of goes out the window, and we have to use more time-consuming SPICE simulations to evaluate the converter. So we have to address that when we're doing the optimization. So now we can define a converter individual as a set of geometrical parameters of the transformer. We have the number of windings, number of layers, width of the copper, height of the dielectric, describes the transformer, and then we have some circuit parameters, which are the resonant parameters, in addition to models of the active or the semiconductors. So we'll run a FEM simulation to get the lump parameters of the transformer, and then we run a SPICE simulation to get efficiency, output voltage, and have an idea about the density. We used a genetic algorithm, replicates sort of evolutionary development. So now we have different converter individuals who will be combined to make an offspring. They're all competing in terms of fitness, efficiency, and size. And then that makes the new generation, and then we repeat the cycle. So interestingly, we can see here we have increasing efficiency and size going down. And as the dark goes to light, the dots, we have increasing generation numbers, and we see that they go down to form this front in the area that we want. So if we look at that final generation, so we have an efficiency of above 80% with a certain size, and we prototyped several of them, tested them experimentally. The fourth prototype is the one that has a double the resonance frequency of the switching frequency. And then we took the fourth one, which had the best overall efficiency and best performance to use in an application. And we did just that. We had the prototype run with 4 Cree drivers with different output power needs. We can see the output power with a very nice sleek load line and a total efficiency of 80-81%. Pretty good over the overall operation. So that was sort of proving the concept. After the PhD, I continued this work a little bit to look at what the integrated prototype could look like. So I'll just give a brief overview of that. So we redesigned it with 3 millimeter insulation, targeting a 15 kilovolt RMS operating voltage. So we'll have the primary side, the PCB. Here we have the gun chip. making it a very, very compact solution because all the electronics are inside, and the rectifier. And then we make a stack up using printed parts to hold it all in place. So we have the Teflon, the coils, we introduce some magnetic material for shielding the electronics, and then we have the inverter and rectifier on either side. And you can see the sort of current mock-up. Due to COVID and sourcing issues, this work is not finished yet. So with that, just quickly conclude that we had a planar transformer design, coreless, that we could show could provide medium voltage insulation, also using this permittivity field grading to improve the dielectric performance. Because of the large leakage inductance, we choose a resonant converter topology with a few passives, high density, and that could ensure soft switching despite the changing output power. So with that, I thank you for your attention.
Thank you very much. So, any questions?
If you back to your graph regarding the efficiency is very low actually for this type of a converter. What is the main reason? Because this type of a this type of a converter should have a normally high efficiency, but it seems due to this core that you have used, or it is due to the transformers or gallium nitride that you have used. What is the reason?
So there are several things. One reason that there's a large discrepancy between the experimental efficiency and the simulated efficiency is for a large part the gallium nitride. So I have a hidden slide somewhere now. So the simulated operation would be 5-6% higher. A part of it is output capacitance losses, and then there's the nonlinear dynamic on state. We're operating at very high frequency. We're also operating the chip from Texas Instruments outside its data sheet. Stops at 5 megahertz, I think. But a lot of the losses are in the gallium nitride. Other than that, you could optimize it for the passives to have less resistance. Did I touch something? There? Yeah. For the medium voltage converter, the efficiency of this one doesn't matter. So for the overall converter station of a medium voltage, I mean 80% here, it doesn't matter. As long as thermally this is sound. So that would be more the issue, or what would be seen for the integrated prototype is whether or not that could be sustained. Yeah. Thanks.
Yeah, basically, you're only losing 2 watts here. So, in the worst case.
Worst case, yeah. Yeah.
Yes. Any other questions? Okay, I think time is 12 o'clock, so thank you very much.
Thank you.
So the final presentation will be made by Keijo Jacobs, and the title is Performance of Charge Carrier Lifetime Tailored High Voltage Silicon Carbide Pin Diodes. Keijo couldn't make it here because he's in Canada, but he has recorded his presentation and we can enjoy it now.
Hello and welcome to my presentation on the performance of charge carrier lifetime tailored high voltage silicon carbide PIN diodes. My name is Keijo Jacobs and I had the pleasure to do this project together with Mietek Bakowski, Per Ranstad and Hans Pitane. It's part of my PhD, and this is just a small section of the work that has been done. Most of it will appear in IEEE transactions on power electronics. This is the presentation content. I will first give you an introduction to the converter and its functionality, the device structure of our silicon carbide diodes and the methodology. And afterwards, we will have a look at the diode performance, a loss analysis, and I will give you a summary at the end. You can see here an LCC converter, which is high voltage and high frequency. We operate this converter above the resonance frequency of the resonant tank of the converter. Output voltage is 5 kilovolt and the switching frequency is 50 kilohertz. The input converter was previously optimized using silicon carbide MOSFETs. This work was done by Untitled. Then we have the resonant tank here. We have the transformer. The design has been discussed previously by Per Ranstad. And this work is on the optimization of the diode rectifier using 10 kilovolt silicon carbide diodes. Previously, a stack of 8 silicon diodes was used here. The particular focus of this work is on the high frequency performance of these diodes. Let's have a look at the converter operation. At the input converter applies a rectangular voltage to the resonant tank. You can see here that the switching of the semiconductors results in a very sharp DVDT, and the resulting current can be seen here. For the diode rectifier, this results in these voltages and currents. You can see here the voltage of the diode D1 and the voltage of the diode D2, as well as the current. As you can see here from the current, a small part is cut out. This is due to the winding capacitance of our transformer. This winding capacitance is inevitable, but it can be tailored. And every time the current direction reverses here, the winding capacitance has to change its polarity. And during the charging, it requires the charge QCP that can be seen here. This results in a low DVDT for the switching of our diodes. As you know, the reverse recovery of the diodes occurs when it switches off. So for example, for diode D1, it occurs right here. The idea is now to tailor the reverse recovery of the diodes such that the peak and the tail occur during a low VD1. This we call capacitively assisted switching, and this results in lower switching losses. We don't call it soft switching because there is a certain voltage present, so it's not entirely soft switched, but it's, let's say, softer switched. Now for the rest of the presentation, let's only look at the diode rectifier and neglect the rest of the converter. And for the process of turning off the diodes, I have marked the different currents that occur in the diode rectifier in different colors here. For example, the reverse recovery is in blue through the ideal diodes. The charging and discharging of the parasitic capacitance of the diodes here is shown in green and orange. And the charging of the winding capacitance CP is shown in purple. Now we can have a look at the switching transients in detail. For example, during turnoff of VD, the voltages increases very slowly, caused by CP. Then we have the charging and discharging of the parasitic capacitance of this diode. This process is a lossless process, which means that the charge of these capacitances gets moved from one capacitance to the capacitance of another diode. Therefore, this only contributes to reactive power. On the other hand, the reverse recovery, which is shown here in blue, is a lossy process. And if we superpose all of these waveforms, we get to this waveform where you can see the reverse recovery with the peak and the tail, superposing the charging of the parasitic capacitance of the diode. And during turn on, the parasitic capacitance discharges again. Now let's have a look at the device structure of the diodes that we used during the study. We used device B, which is a conduction optimized diode. Typically, the lifetime for these diodes is below 1 microsecond due to carbon vacancies in the silicon carbide material. Therefore, a novel charge carrier lifetime enhancement process was applied. This consisted of carbon implantation and simultaneous thermal generation of Frankel pairs. This is illustrated here in the figure. You can see the carbon implantation from the anode side, and then the generation of Frankel pairs throughout the whole diode. Maybe I should mention that this results in a higher charge carrier lifetime here closer to the P+ region. Then we have device C, which is a switching optimized diode. For this, we require a low charge carrier lifetime, and therefore we applied a proton irradiation process. You can see the effect here in the schematic. The protons come to a halt close to the N+ buffer. Therefore, we expect a lower charge carrier lifetime close to the N+ buffer. I should say that device B and C were chosen from over 100 differently optimized diodes as two extremes, a very conduction optimized device and a very switching optimized device. There's also a comparison device A and a silicon implementation, but I'm not going to detail them here too much due to the time restrictions for this presentation. Now we're going to have a look at the packaging for the different diodes. I show here the silicon diode, of which we need 8 in series. Then device B, which is the conduction optimized device, is packaged in this kind of package. And device C is soldered on the lead and then bond wired. Now let's come to the methodology that we used for our testing. We ran into several issues measuring the diode performance. The problem is that the characterization of diodes via a double pulse test does not reflect the diode's performance in a soft switched converter. For example, voltage probes need to measure up to 10 kilovolts, but the resolution of the oscilloscope is only 256 bits. Therefore, we only get 40 volt steps in our measurements. Therefore, the on-state voltage cannot be measured electrically. Secondly, the lossy reverse recovery current and the lossless capacitive current, they superpose as shown before in the figure. Therefore, the switching losses cannot be measured electrically either because we cannot separate both. The idea was therefore to measure the losses calorimetrically, but this imposed new challenges. For example, the device temperature was unknown and the separation of conduction and switching losses was no longer possible. The final approach was therefore to combine calorimetric and electric measurements with device and circuit simulations. This is shown here. And just to go through it very quickly, we ran a converter test, which is a calorimetric test. We measured the increase of the temperature and then deducted the diode losses, the total diode losses, and the junction temperature of the diode. We could use the junction temperature in the operation point then to do IV curve measurements at the specific temperature. Feeding the IV curve measurements then into an LT SPICE simulation, we could get our conduction losses. Then we did a second test, which is measuring the switching dynamics of our circuit. We also preheat the devices to the junction temperature and then operate the circuit for a very short time. Therefore, self-heating can be neglected here. And then the measurements can be fit to a TCAD model. And the TCAD model helps us to analyze the reverse recovery losses in detail. Here you can see the laboratory setup on the right. And in detail, the diode rectifier in a foam enclosure for the calorimetric measurements. The diode was let into transformer oil, and the transformer oil was constantly stirred by a magnetic stirrer, which was located below the PU foam enclosure. Then for the electric measurements, we removed the PU foam enclosure. We preheated the oil to the desired temperatures and then measured via a shunt and a voltage probe. Now let's have a look at the diode's performance. Here you can see a measurement of the reverse recovery. Well, in general, the switching effects of the diode for the conduction optimized and the switching optimized device. The voltage is shown here in red and the diode current is shown in blue. This is obviously a zoom into the switching performance. So the whole conduction performance is totally out of scale out of this graph. As you can see for the conduction optimized device, we have a very high reverse recovery peak. And then we have a tail. You can also see the capacitive charge, which I marked here in green and in orange. We measured for room temperature and for the temperature at the operation point, which was 72 degrees Celsius. For the switching optimized device, you can see a much lower reverse recovery peak and a shorter tail. And therefore, we can expect a better switching performance and lower switching losses for this device. The measurements were then taken and fit to a TCAD model. You can see in blue here the same measurements that I showed you before. And then in green, the fit of the TCAD model. And the charge carry lifetime distribution that yielded these results is shown here. You can see for the conduction optimized, the high charge carry lifetime coincides with the carbon implantation. And for the switching optimized device, the low charge carry lifetime coincides with the stopping zone of the ion implantation. The TCAD model can then be used to analyze the dynamics within the semiconductor. We can see here the whole concentration plotted over the distances from the surface of the diode. So the P+ region is here on the left, then the N drift region is in the middle, and the N+ buffer is here on the right. You can see for the conduction optimized device, the whole concentration is decreasing quite uniformly, but slowly. And for the switching optimized device, you can see that the whole concentration decreases much quicker at the N+ buffer. And comparing the time instants here, for example, at 7 and 8, you can see that the whole concentration is completely gone for the switching optimized device, whereas as at 7 and 8 here, there is still quite a lot of holes present in the semiconductor. Therefore, switching with the switching optimized device is much faster. Let's now analyze the losses of the diodes. I prepared this table, which is a bit big, but we will go through step by step. I compared here the silicon stack, which is the state-of-the-art implementation of the diode rectifier, to device B, which is our conduction optimized device, to device C, which is our switching optimized device. All of these comparisons are done at the operation point, which can be seen here. The calorimetric measurements reveals the total rectifier losses. You can see comparing the conduction optimized device with the silicon implementation that we achieved a loss reduction of 37%. The comparison is not entirely fair because the silicon carbide device is a 10 kilovolt device and the silicon stack is only rated for 8 kilovolts. So if you would interpolate linearly, you would get a reduction of losses by 50%. For the switching optimized device, we only get a reduction of 12%. Then let's have a look at the results for our conduction losses. These were achieved by using a measured VI curve that can be seen here on the left and feeding this into an LT-SPICE simulation. We can see that the conduction losses we get for our silicon implementation is 5.3 watts, whereas for our conduction optimized silicon carbide device, it's only 2 watts. And even for our switching optimized silicon carbide device, it's 2.8 watts. We then simulated also the conduction losses and additionally the reverse recovery losses in the TCAD simulation. You can see that the conduction losses coincide with the values that I've presented for the previous method, approximately. However, the TCAD simulation gave us the opportunity to compare the reverse recovery losses also. And you can see here that 19% of the total losses are reverse recovery losses, with reverse recovery losses being 0.4 watts for the conduction optimized device, and 3% of the total losses are reverse recovery losses for the switching optimized device, where the reverse recovery losses are 0.08 watts. This indicates that the switching optimized device C could potentially be used for an operation at much higher switching frequencies. However, we haven't tested that yet. Now I'll give you a summary with some takeaway messages of this presentation. Number one, applications with high output voltage often require series connected semiconductor devices. A single silicon carbide device can be a competitive alternative. Number two, a hard switch characterization of semiconductor devices does not indicate the performance in a soft switch converter. Therefore, we came up with this rather extensive method of testing. Number three, The LCC converter inevitably features a softer switching of the rectifier bridge. Therefore, we can tailor the reverse recovery length to fit the voltage waveform for reduced switching losses. And we found out that the topology with the transformer that we used favored short and high reverse recovery over long and low reverse recovery. A good fit for the application turned out to be the conduction optimized device B, which was treated with a novel process. The losses decreased by 37% compared to a stack of silicon diodes. I would like to thank all the collaborators here that are listed here. And if you have any questions, I'm sure Mirtek and Per and Hans-Peter will be there. If you want to have answers to more detailed things, then you can contact me at this email address. Thank you very much and enjoy the rest of the conference.
So this concludes our session on medium voltage converters, and now it's time for lunch. But before we go to lunch, I will just tell you that we meet here again at 2 o'clock, and then Claire Troadec will give us a market overview for gallium nitride and silicon carbide power devices. I'm sure this will be very interesting. So enjoy your lunch.
Your woman try to do her best. Every time your best friend come in